Definitely not just because they were given a random afternoon off. I'm sorry to disappoint you.
Such a dangerous place. I know we're going to be recording. Everyone is basically there, but I'm going to answer the link. You
ready to go? Yeah. Okay, hi everyone. So today we are very lucky to have Chris Akers here all the way from IAS. He was at PhD student here, he's returning. Telling us about multipartite edge mode and tensor networks today. Take it away.
Thank you, Phil, and thanks everyone for inviting me. It's been a great year so far, and I'm here till the end of the week, so I look forward to more discussion. So this is a project that might give some of you deja vu from last year. When I was at Berkeley 11 months ago, I talked about sort of the beginning of this project, some of the questions that were motivating us, and some of our ideas for solving them. And this talk is the completion of that. I'm going to tell you what ideas worked out and what's resolved. So, okay, we've learned a lot about quantum gravity by thinking about ADS-CFT. I think that's not contentious in this room. For our purposes, we can think about it as follows. So there's sort of two Hilbert spaces. One in which I can think about a time slice, sort of like this disk. And the other one, the time slice is like the circle, the boundary of the disk. And on the disk side, that's where gravity is. We have maybe some state psi ADS. And then there's a map V, some linear map that relates that maps you to some state in the CFT Hilbert space that here we're calling a cyclone. So there's this holographic map V, and we'd like to understand its properties and so on. That's part of what it means to understand ADS-CFT. And our understanding of ADS-CFT is still imperfect. So that's kind of where we are now. A lot of questions we'd like to answer. We're making progress, but let's say generic state black holes, what happens when you dive into them, it's still a little bit of a mystery. So one path towards studying holography is to think about these tensor networks, which are just toy models of the ADS-CFT map V. And it helps to think about them, because building better tensor networks, better toy models, forces you to really think about the properties that ADS-CFT has and how they can fit together. So by trying to build these toy models with various properties like a holographic entropy formula and reconstruction like ADS-CFT has, we learn things about holography. So what are tensor networks? The details of the traditional discussion are not going to be that important for us, but this is the overview. So you kind of start with some discretized bulk. It's discretized in sort of the way this picture represents. So you have these vertices and you have these links between vertices. And at the vertices, you might imagine there's some qubits, so there's some d-dimensional Hilbert space. And that's like the matter degrees of freedom in ADS. And then between them on these links are entangled qubits. So I don't think you can really see it, but there's sort of a solid line, another solid line, and they're connected by a dotted line. I don't think you can see that. But so that dotted line is indicating that that's entanglement between these two qubits. And these are going to be qubits, let's say, with much larger dimensions. So these are just finite dimensional Hilbert spaces, say a much larger dimension than what's on the vertices. And this is our sort of discretized picture of the book. And then the rest of the model is that you obtain a dual boundary state by acting with a tensor at each vertex. So what you do is you sort of take your discretized bulk, and then everywhere I've boxed, I put a little red box. I'm sort of circling 5 Hilbert spaces. So let's say in this one, there's the qubit, that's the matter qubits, and then 4 qubits of larger dimension that are associated to the geometry. And we're taking that tensor product of 5 Hilbert spaces, picking some state there, maybe it's a random state, that's a good model, and then we're just hitting it with the bra of that state. So we had some state, which was some ket on all of these degrees of freedom, that we're hitting each of these things in the red boxes with some bra individually, so we localize the network. That's the special structure that we call a tensor network. That's the V, and it leaves you with just the remaining part of the ket is these Hilbert spaces. Okay, so that's something that looks like it's on the boundary. That's what we're going to call the boundary Hilbert space. We have some state there. So that was the map from this Hilbert space now. That's the traditional construction of tensor networks. Now, they have pros and cons. One pro, maybe the biggest thing to like about them, is they satisfy a kind of holographic entropy formula, which is very much like what you get in ADS-CFT. So the holographic entropy formula says, let's say you selected some region of the boundary, say this solid blue part, we're going to call it capital B, and you picked some state psi in the bulk Hilbert space, and then you mapped, that's a state on the qubits at the vertices, and then you mapped that state to some boundary states. You traced out all the parts that aren't intersecting this blue region we're calling B, that leaves with the reduced density matrix on B. Plug that reduced density matrix into this formula, that would be the von Neumann entropy. And it turns out that in these networks, the von Neumann entropy satisfies this holographic entropy formula. So this von Neumann entropy of this boundary reduced density matrix is given by this minimization over this quantity here, where what you're doing is you're considering all cuts through this network that are homologous to B. So maybe this one, so that's the in on the boundary of B. But here we're cutting these links, but we also have to consider paths that say cut a different set of links. And for each path, we consider the log D, which is the dimension of the geometry qubits, times the number of links that we're cutting. That's this piece here. Add to that the von Neumann entropy of the matter qubits that are bounded by the dashed blue line, the solid blue line. That's this von Neumann entropy here. Add this together. That's this quantity that, in the minimum value of this over all cuts, gives you the boundary. That's very much like the Free-Tucky-Martin formula, the quantum corrected one in ADS-CFT. That's a pro. That matches ADS-CFT and gives us some intuition for what's going on in ADS-CFT. But a big con, the con that will concern us today, is that you don't, in these traditional constructions, have a duality of local Hamiltonians, at least not in an obvious way. And what I mean by that is, in ADS-CFT, part of why it's so nice is that it's a dynamical duality. So time evolution in the bulk in a deep way matches time evolution in the boundary. And both have this local structure. Both are local theories in a reasonable sense. So let's try and realize that here, and it will fail. So let's define on the bulk Hilbert space some Hamiltonian that, let's say, is a sum of local terms, where maybe each term couples nearby qubits. Good, so that bulk Hamiltonian is local, but now let's map it, let's consider one of those terms, it's local, map it to the boundary. So we're just conjugating it by the map. And in general, it's going to be this incredibly non-local guy. So the Hamiltonian that you get on the boundary by pushing the bulk Hamiltonian through the map is, in general, incredibly non-local. And this is an undesirable feature. It's not really a duality between local Hamiltonians. So, yeah.
Just question. So, there's many Hamiltonians, right, that have the same action on the code substrate. Like, is there an argument that shows that none of them?
No, good. So, you could start making some choices, and you could especially start adding some degrees of freedom that help you make it local. But there's an inherent tension actually between local duality and this property here, where because of this, you have this entropy formula which we like, and it leads to these reconstruction properties which we like, and that means that this operator here, which is kind of localized in the bulk, it's reconstructable even if you erase any sort of small patch of them. And So it's sort of necessarily smeared out in a non-local way because of the error correcting properties. So there's this inherent tension.
Sorry, Chris, I'm confused. I mean, generally, Hamiltonian or not, we expect that local operators in the bulk get mapped to non-local ones in the boundary.
Yeah.
That is a true feature of ADS-CFT.
That's right.
Why are we complaining that the tensor network should reduce that feature?
Good. As I'll say in the next slide, right, we want operators in general to be mapped in this error correcting way, but we somehow also want this thing which seems to be in tension with that, which is this duality between local and Hamiltonians. And so what's going on? So, yeah.
What is H-bulk?
H-bulk. Here, H-bulk is something I'm just defining as an example, which is a sum over local terms. Local, like Hermitian.
Can you say again why we want, what do you mean by the duality between local and Hamiltonians, and why do we want? I missed that.
Yeah, I want something like ADS-CFT where I can write down some local description. The theory is local in some description. So I can write a local Lagrangian that describes ADS dynamics.
I mean, we know that there is a CFT Hamiltonian.
Exactly.
So you're complaining about the fact that I don't get that by pushing the Hamiltonian out. What does that even mean?
I think my next slide is going to clarify exactly this question. The ADS-CFT doesn't work this way because it's gravity.
Yeah.
So the Hamiltonian doesn't have the structure where.
So I think there are some papers using Hamiltonian simulation techniques to construct local.
By people in this audience, in fact. So you can, right, so to comment on that, you can just take this structure, push it to the boundary, and then use these gadgets or some other techniques to make this more, to make this local. Essentially, that's not going to look like gravity, though. And so if we want to model gravity, that's not going to give it to us, would be my claim. Okay, so I think, let me address Raphael's question by going to the next slide. So long term, we would like to include time evolution while keeping the holographic entropy formula. So let's ask why our tensor network is having this problem, while ADS-CFT doesn't. So the big difference is that in ADS-CFT, the bulk Hilbert space is very different from what we have in tensor networks. We have gravity. So, and in gravity, there are constraints that reduce the Hamiltonian to a local integral along the boundary. So it takes something like this one. And this leads to an easy match to a local Hamiltonian in integral theory. That's the difference. It's very simple. It's just this is setting up the idea that as a step towards adding time evolution into tensor networks, I think that what we should do is try to incorporate a more sophisticated bulk Hilbert space with more gravity-like constraints.
Bulk time evolution, what they're talking about is just a three-dimensional, and of course you're not putting anything in the boundary.
That would be the really quick evolution.
Yeah.
But
Is that what you mean?
I want ADM Hamiltonian as well. But yeah, I want.
It's totally different.
Right.
Two are totally different thing.
Right, that's right. Yeah, it's the ADM Hamiltonian that matches this would be the ADM Hamiltonian.
Yeah.
This is the thing.
So you don't want to, you're not doing like the equivalent. There is different equivalent tensor that all corresponds to the same boundary states.
Right.
That's not the way you do it, is it?
Yeah, I mean, looking ahead, what we won't have really good evolution. We'll basically have a tensor network that models the entire really good patch. So time evolution is just there's only ADM evolution. Yeah.
And yeah, I guess it's on the same line. When you said that you want a bulk local Hamiltonian and a boundary local Hamiltonian,
Yeah.
I guess what exactly do you mean by bulk local Hamiltonian? It's not the Wheeler-DeWitt Hamiltonian. You're talking about the ADM Hamiltonian, but is there really a local Hamiltonian for the bulk one?
Yeah, so the concrete statement that I want to make is I want time evolution in the bulk that looks like time evolution in gravity. So this will be taking a step towards that. And I would say
with the ADM Hamiltonian.
Yeah, I would say when you consider, yeah, it'll be like the ADM Hamiltonian. That's like the evolution rate. So.
In the book, is that a local? Like, can we think of that as a local?
No,
it's
with the Wheeler-DeWitt Hamiltonian, you can repackage everything and then it's equivalent to some local theory defined by local Lagrangian.
Okay.
That's the sense in which they're both.
So the gravity part of the bulk Hamiltonian would be this boundary term. But I just have some other fluid theory. Do we think like in quantum gravity that's also just a boundary term, or?
Yeah, they get added into the Hamiltonian constraint.
Okay.
Their time evolution gets added into the Hamiltonian.
I see.
So,
So it all counts.
yeah, so the physical time evolution is still this, and then the time evolution that you might think of as field theory evolution. Really good. Okay. Good. So now at first it might seem intractable to make tensor network bulk over spaces look more gravity-like. And the reason is just that they inherently involve some discretization of space-time, which would break the very diffeomorphism invariance we would like to have. That could be important. However, in 2+1 dimensions, there's a trick available to us, and this is the dimension that we'll work in. And we can change variables. So this is a well-known thing since the 80s. So the change of variables isn't very important, but it looks something like this. So you define a gauge field A that's some combination of the Weyl and the spin connection. So these are the generators, translations, and boosts. And the indices are contracted in the appropriate way. That's what the dot represents. And if you do this at the level of the action, the theory transforms from the Einstein-Hilbert action to one of a Chern-Simons theory. It's with an SL2R cross SL2R gauge in HEP-QIS. So this is a topological quantum field theory. And now, in this TQ of T description, discretizing space-time doesn't mean breaking gauge invariance. Now, so that's going to be our basic plan. Some of you might worry, but we're talking about using Chern-Simons, something like Chern-Simons, and then discretizing. But this is known to be very difficult. There are anomalies that show up in general. That's actually not a problem for this particular kind of Chern-Simons theory. Essentially, these SL2Rs have equal and opposite levels. This is a parity invariant Chern-Simons theory. And you can show there are explicit constructions where, like this zero triad construction, that can put it on OS. So it's not one instruction for this kind of Chern-Simons theory. But we won't really be using this explicit Chern-Simons theory, so it doesn't matter either way. So the idea is, we could try to incorporate this discretized TQ of T into H-bulk, and on some level that's straightforward. A number of recent papers have added gauge fields and considered non-trivial link entanglements. However, we'll run into new subtleties. The TQ of T description describing gravity is more sophisticated than the gauge theory so far incorporated into tensor networks, and we'll need to figure out some changes to the tensor network. So, let me explain the main subtlety that we're going to address. There's a couple, but I think this one was the most interesting to attack. So, recall in ADS-CFT we have the holographic entropy formula, which I explained before in the context of tensor networks, but this is what it looks like in ADS-CFT. So your minimite to compute the boundary entropy of B, say on a time symmetric slice. It involves this minimization over the area of some surface, the area plus the entropy between the boundary region and that surface. What's important is that in the TQ of T description, it's different. It looks different, but you're totally allowed to use the TQ of T description in this holographic entropy formula. So what's different is that we have changed variables. So now what was the metric is now some function, is some property of the gauge fields. And the gauge fields are living themselves on some metric, but that metric's not important. So it's like there's a world sheet metric and a target space metric, and it's the target space metric that matters for this formula. So when there's no matter around, this theory is topological, and if you were to compute in the gauge theory, this topological quantum field theory description, the entropy of this boundary region B, what you would be doing is evaluating the expectation value of some Wilson line. It's in some representation with some boundary conditions. This was worked out in 2013. And because it's topological, if there's no matter, it wouldn't matter if we're evaluating this Wilson line following this path or that path. So this is just, I draw this here to really emphasize that it's not, in this description, it doesn't matter the path that this area operator is following. What matters is the gauge fields along the path. Okay. So the area operator looks different in this description. Yeah.
Is A hat the log of the Wilson line?
Yes, I think that's right. Okay, so we want to make a tensor network model of this. Excuse me. And we still want to have a discretized geometry. We're working in the paradigm of tensor networks. And we want some gauge theory like this living on the links. But what's different, again, is that now we want the A hat operator to measure the gauge fields only, not care about the geometry. This is an abnormal thing to do in tensor networks. So to emphasize, in the case where we don't have matter in our block, then A hat should be the same answer evaluated at any cut. When we do have matter, it will depend on, this area operator might be more minimal to avoid that matter or include it. So those are the choices they would have to make. So our main result, our technical result, is to construct a tensor network like this. And it turns out thinking about this problem doesn't require the full complication of working with this SL2R plus SL2R transcience theory, which is complicated for a number of reasons, including it has a non-compact gauge group. Yeah.
These pictures, the space, the disk itself is not the same space that we had before, right?
That's right. That's right.
And so how do I think of that space and how do I map this back to the original problem?
That's exactly the right question. So
what happened to locality, for example? Something pretty drastic seems to.
Yeah, that's exactly the right question. So here, in this description, the original geometry is very obvious here. And that's really all I'm going to tell you in this talk. But the dictionary is...
How is this better than just the boundary description we had in the first place, I guess, if I wanted to?
We are going to have matter that is holographically encoded. So there's going to be matter, it's going to be moving around.
For which you have a local bulk interpretation in the original metric?
Yes, there is going to be one. But to tell you, there's just some dictionary. It's like the local bulk that we're used to is like some target space that's simpler than the holographic matter, that part. So there is a local bulk description that we're used to, but what we're working with here, this tensor network is looking at the topological quantum field theory description, which you might imagine is, it obfuscates some of the original geometric. But it's still going to have a holographic entropy formula, for example. That's not true.
So there's going to be some map that takes me between the two descriptions that makes it manifest how to recover locality in the bulk.
That's right. So in principle, what you would have is the nice normal graph description that you're used to. There would be some dictionary between that and this description, and then it would be in this description that the holographic map acts in a nice way. That would be, you might imagine it as a proposal for how to think of the holographic map.
But the locality of the Hamiltonian on the lattice does not imply in any way locality of the Hamiltonian in the bulk, right?
That's right. That's right. So what will happen is that, the reason we care about this is because it's easier in this description to construct Hamiltonians that manifest and reduce to some local boundary. And then those will map to Hamiltonians in the other description that are local boundary intervals. So what I wanted to say at this bottom point was we're going to work with a simpler topological lattice gauge theory with which we can analyze adding in this behavior without working with the subtleties of, say, non-compact behavior. So what is that new topological theory? So it's a very simple one. Maybe the simplest one we can think of. We're just going to consider, first of all, finite group G. And we're going to define a Hilbert space, HG, which is, you just consider for every group element there's a ket. They're orthogonal to each other for different group elements. And the Hilbert space is the span of all those cats. It's a well-studied Hilbert space. And you might imagine that Hilbert space corresponds to one link, one oriented link. And we're going to consider now some network of these, so a network of oriented links, or a lattice setting. So this is like the construction of some lattice gauge theory. Let's say there's n links, so n copies of this Hilbert space, that's what I've written here, arranged in some way like this. For the moment, the Hilbert space doesn't know anything about the spatial arrangement. Now, I'm also going to include matter legs. I'm going to draw the matter legs like this. So, for generality, I'm going to allow some vertices to carry matter, other vertices need not. So here I've drawn these two have it, so they're like diagonal legs with some gray dot at the end. That's indicating that this vertex carries some amount of degree of freedom, which I'll explain in a moment. Could in general have electric or magnetic charge. Now, on this Hilbert space, we're going to introduce two constraints. The first one is very familiar. It's the Gauss-Level constraint. And essentially, so here drawing without matter, what happens is, if you just look at one vertex, you could say, imagine there's some assignments, you have some wave function over the assignments of group elements to each link incident to that vertex. And Gauss's law says that this wave function is invariant under shifting all of those group elements in the appropriate way by the same element here in G. So if you were to look really close, you would see the ones oriented out are left multiplied by G, the ones oriented towards are right multiplied by G inverse. That's just how the rules work for constructing these lattice gauge theories. Not really important. So the lattice is invariant under shifting all links at each vertex by some group element. So for each individual vertex, you can do that shift. The wave function is invariant under that. Flatness is a more novel constraint. It's not one that people often consider as a constraint. So what it is if you zoomed into any plaquette, which is any, say, smallest square. So not like a square that you could build out of other small squares, but like one of the fundamental units. Then to each link, there's some group element assigned. And the product of the group elements as you go around the square have to multiply to the infinity. And if you move with the arrow, you're acting with that group elements. If you go against the arrow, like here you can see H3 is oriented against the path. H3 gets an inverse for that reason. But the product of group elements along the path has to multiply to the infinity element. Yes?
Well, let's say in the original Saltor by a Saltor case, would there be some condition that corresponds to the ADS background metric?
Would there be some condition that corresponds to the ADS background metric? Yeah, there would be some state that would correspond to meeting the ADS background.
I think the flatness condition in SL2R times SL2R implies that you have an ADS background metric.
Oh, thanks.
Actually, the flat, this is a kind of weird twisted version of those variables where both of these become flatness in the original Chern-Simons variables. Yeah.
Okay.
Yeah, I was suspicious about flatness as well.
Yeah, in Chern-Simons flat, it's these sort of get used to. Yeah. So this is a toy model where there's sort of separate constraints that we're imposing. Okay. So these are the two constraints, and we're defining our physical Hilbert space as this pre-gauged one that was just tensor product of all these guys, modded out by those constraints. Citing the tie here, I think that's the first place I've seen the discussion where he defines a very similar Hilbert space. Like this is the ground space of his quantum level model, but he doesn't really impose these constraints so much as if they're satisfied in the lowest energy subspace.
Question.
That's the model. Yeah.
How are you designing the directiveness of the?
Good. So I like to just assign some direction to any link, and then you go from there. So yeah, it works for either way. Any orientation of links will work.
Gauss constraint is a gauge constraint.
Yeah.
And what was the flatness?
Flatness I'm also imposing as a constraint. It's this condition. So I'm just saying. Yeah. So I'm just projecting onto the subspace that satisfies this.
Yeah, but what's the origin? What's is this?
Oh, in the continuum case, it's like f mu equals 0, or fij equals 0, or ij are the spatial components.
Yeah, but that's like physically what? Is it like really like,
Oh, it's-
area goes to 0 and that's short? I mean,
It's flatness of the connection, so it doesn't have to be 0, but it has to be a flat connection.
is it
That's why
equivalence
it's
principle?
Say again?
Is it like something like equivalence principle? I don't know what.
Oh, it's
what
like-
it is.
In these topological field theories like Chern-Simons, they have, like Chern-Simons has this constraint as well, fij equals 0. Right, Luca, do you want to comment?
Well, I guess I was just wondering, it's in Chern-Simons, it's not a constraint. It's a solution to the equations of motion that's imposed as a constraint in the path. That ends up being imposed as a constraint in the path integral. So I'm just wondering why in this construction it's a constraint on the Hilbert space.
It is a constraint on the Hilbert space.
Fij is a constraint, right? Fij equals 0, or ij or something.
Well, it's kind of in JT, right? R minus 2 is like an equation of, sorry, R plus 2 equals 0 is an equation of motion that ends up being a constraint when you do the path integral. But I don't know if the space of all metrics should satisfy R plus 2 equals 0 locally everywhere. I guess you could construct this Hilbert space and.
Like, when you set up the Hilbert space, the path integral into a Hilbert space interpretation, you have to impose certain of the equations of motion as constraints because they are the relationship between initial data of the theory. Fij equals 0 has no second derivative. So it has exactly a relationship between stuff you put on a Cauchy space. So it is so in the Hamiltonian interpretation, it is a constraint.
I see.
So exactly what Gauss law is actually. It's in the same place.
JT is really constraint. JT is really constraint, right? Because it's just a linear delta function. But not the equation motion view.
Yeah. John?
You started off by, I got the impression that you were going to go where you were imposing the full, the full width equation to get a boundary Hamiltonian only. So it doesn't sound like you're doing that yet, or?
No, yeah, this is my toy model for the topological field theory. So I won't say any more about it. Yeah.
But why does this get? Are you trying to go there?
That would be that's the long-term goal, not the project of this work. The project of this work is to get the tensor network that has this different kind of area operator in the holographication formula. Yeah.
I want to make a comment on that. So in the Chern-Simons rewriting of gravity, Fij equals 0 is where the Hamiltonian constraint and all the different of constraints are. Okay, so basically these are toy models for the Fij equals 0 constraints, which these are toy models for the constraints, but like the thing we're toy modeling are the diffeomorphism constraints of the gravity.
And then do you get the same thing that you have, that you're in an energy eigenstate, or because it doesn't feel like you've projected far enough to get to be living in an energy eigenstate.
It would be like each of these states would be analogous. I mean, it's very different from the Hilbert space of SL2 or SL2 or Chern-Simons, but it would be analogous to like the full Billiard hash. If that makes sense.
I mean, it might not to be.
Good. Okay. Well, this yeah. Good job.
So just one more question.
Yeah.
This flatness condition you imposed both when you insert matter and without matter.
Yeah. Thank you. So with matter, both of these change. So if there's matter, say at this vertex, then this guy, the wave function is invariant under a shift like this with the matter.
Also
There's also
expressed
some
by G.
representation of the matter. Here it's the same, but the magnetic charge of the matter is what's relevant, and it shows up by modifying this constraint. So it doesn't have to equal. In effect, it's like this product doesn't have to equal the activity element. Good. Okay. So operators, let's talk about those. So what's available on each individual link? So one of the HG. There's two basic types. What you don't really need to know much about them, but the two types are like this kind of shift operator. So this LH, H is group elements, axion ket G, G was group elements, by left multiplying group element by H. And the continuum, this is like an electric operator, or like the exponential of some electric geometric operator. These W's are like the Wilson operators, or you make a Wilson line out of multiplying many of them together, contracting all these I and J indices. That's what you get in the continuum. It's like a Wilson operator. And they're labeled by mu, which is like an irrep of the group. And these I and J are like indices within the irrep. So this W acting on G gives you this this state. So it just multiplies it by this D is the muth representation. I and J are its matrix elements. So this is sort of a conjugate operator to L. So that's kind of what you have available in each link, but when we impose both of these constraints, neither of these, localized to any general link, are physical, because they don't compute with the constraints. So we have to build gauge invariant operators out of combinations, and these combinations have to act on different links. So for example, Wilson lines would be built out of a combination of these guys that ends only at the boundary. Somewhere you don't impose Gauss's law. And the most relevant kind of gauge invariant operator are these ribbon operators. So this will be relevant for us. Now, here I've defined exactly what it is. I'll tell you what's relevant about it. So, sorry this is small. This is F subscript gamma with two arguments, H and G. Gamma indicates the path. So here, this path is like a thickened line. It's a ribbon, that's what we call a ribbon operator. And so there's two parts to a ribbon. There's the spine, which is kind of the path that follows along. And then also there's what we might call the spokes, these parts coming off. And to indicate that gamma cares about these spokes on this side of the path, that's why gamma's thickened that side. And what it does, so here I've drawn its action. There's a group element assigned to each of the links along the path, G1, G2, G3, H1, H2. And the first thing, it does two things. The first thing is this G here, one of the arguments. Essentially, it's like a Wilson line part. And we've chosen it such that what it does is it looks at all, it takes the product of group elements along the spine, and then it asks their product to be equal to G. So this is a Kronecker delta G times of the product. The other element, H, is acting like the shift operators that act by left multiplication of the group elements, or right multiplication, that's also fine, on the two spokes. And it's doing it in such a way that helps it be gauge invariant. The way it has to do that is it essentially has to, it can't just shift H1 by H. It has to shift H1 by H transported along the spine. So, it's transforming under the adjoint. So it gets, if H conjugated by G1, that's what's left multiplying H1. And then something similar is happening with H2. So these ribbon operators in general, some of them are Wilson lines, some of them shift, but they have to shift every link along the path. If they didn't shift every link along the path, then they would violate the flatness constraint. So the other physical operators, if you have matter around, you can have other ones that consist of matter dressed to the boundary where you're not imposing gauge invariance. In general, dressed with ribbons. So electric charges would be dressed with Wilson lines, dions would be dressed with both, so on. Okay, so let me say something about the subalgebras that we care about. So let's say we have a lattice like this, and I'm going to circle this subregion B, and we want to ask, what are the algebra physical operators associated to this subregion B? There's some choice here. Let me just basically associate to be all physical operators that I said on the previous page that act non-trivially only within B. So for example, one good such operator would be a ribbon that starts at this point of the boundary, and then follows this path, and then to this point of the boundary, all within. The most important aspect of this algebra for us will be its center. And its center, it turns out, this was new to me. I think other people knew this. You can construct it out of the ribbons that we said before. So this particular linear combination happens to be central in this algebra. It's not that important. The ingredients are these F, gamma, HGs are the ribbons we said before. The gammas that they have to follow in general are ones that hug the boundary of B. So here would be ribbons that say start at this point and follow this path, go up here, such that some matter charge that was inserted at this vertex couldn't be dressed in a way that crosses that path, because that could change the value of the ribbon. So what's physically important about these ribbons is this linear combination, what it does is it measures the total net electric flux flowing out of B. So the central operator in these subregions is the ones that measure the net flux through B. Okay. So that's what's important. And this is a little different than if we had just imposed Gauss's law. If we just imposed Gauss's law and not flatness, the story would be different because there would be more central operators. There would be a central operator associated to, say, each of these links of the boundary, and it would be, these operators could tell you how much electric flux is flowing out of this link, how much is flowing out of this one, and so on, individually. So it would be a physical thing you could do to ask, where is the electric flux flowing out of this boundary, this region, and how much? With flatness, you can't do that. Theory is more topological. All you can ask is the net flux flowing out. And that's what this guy does.
What was the chi-mu?
Yeah, chi-mu is the character of the mu theorem. I didn't say that. But yeah, chi-mu is the character. This is sort of it just turns out that this is the linear combination you need to take of the ribbon that I wrote on the last page to get the thing that has the interpretation of the total, the measuring total electric flux. D mu is the dimension of the representation, and this is the total number of neurons. Okay. So looking ahead, we now have the ingredients for me to tell you essentially the main result. The main result is that we're going to construct a tensor network where the central ribbon operators that I listed on the previous page form the area operator. So we'll have something like this. We'll have some lattice, they can have matter, so on, and there'll be some map to just the boundary legs. And we can take some subregion of the boundary, say the ones I've highlighted here in red, called V, and we can compute their boundary entropy. And it's going to be given by this holographic entropy formula, which looks very similar to the ones in other tensor networks. What's different is that this area operator is this ribbon operator that measures the net electric flux. So this will have the property, for example, that when there's not matter, it doesn't really matter, it doesn't really care which path it follows, because the net flux is equally evaluated on any path, as long as the endpoints are there. When there is matter, what it really cares about is whether or not it's including or excluding certain matter. Okay, so this is essentially the main results. And this is the linear combination of the ribbons I said in the previous slide. It's just weighting, those were essentially projectors onto sectors of particular flux, and this is the amount of electric flux. So again, this is different because this A-hat is different.
So if there's no matter, it's just zero?
It's not zero because you could say have flux flowing from boundary leg to boundary leg.
Is this an exact formula or is it in some large...
Oh, it's in some, yeah, it's in some approximation. You need, say, a lot of flux for this to be true. Yeah. So, to argue this, what's important is that there's a sort of lattice independence of this theory. It's a topological theory, I haven't emphasized that, but let me really emphasize that now. So what you can do is you can change the pre-gauge Hilbert space, which was indicated by the lattice, in a few controlled ways that will leave the physical Hilbert space invariant. So in particular, what you can do is, say, take this vertex where Gauss is well satisfied, and you can add a link that splits it apart. And this will not change the physical Hilbert space at all. If the state, there's a completely well-defined map that maps you from, say, a state in this pre-gauge Hilbert space to a state in this pre-gauge Hilbert space. The mapping is exact. The state is just completely equally well represented by both lattices. The physical idea is that there's no operators that can probe that change in the lattice. And so an example of this that might be more familiar is if you had, say, one link, which is associated to this one copy of HG. This is completely isomorphic to two copies of HG modeled by Gauss at the fusion point. So these are completely equivalent Hilbert spaces, as long as they're satisfying Gauss. This is just the generalization of that. This is true even if you just have Gauss's law. If you have the flatness constraint, this stronger thing can be included in this statement. We can also add and remove a plaquette in this sense. So you could take some lattice, some part of it, say, looks like this. You could subdivide this plaquette into two duplicates. Now it will satisfy flatness constraint in both of them. Or if it's satisfied here, it will satisfy in both of them there. You can also go backwards. So if you had some lattice that look like this, you can remove this guy, end up with this lattice. The physical Hilbert space is completely unchanged. So that's a cool feature of the fact that the theory is topological. You can write down everything exactly. And one thing that will be important for us in regards to this is that physical operators change in well-defined ways. So for example, these ribbon operators, under these lattice deformations, just say ribbon operators. So we had this ribbon operator here, acting on this lattice. If you consider the lattice with this link gone, so drawn over here, he's still the same ribbon operator. Now he just has no link to act on here. That's okay. The way he acts on this lattice maps you to a state that is exactly equivalent to the state that you got to by acting this ribbon on this lattice. And we can take these lattice modifications to the extreme. Really to the extreme, and this will be important. So if we started from some lattice like this, there's some vertices that have matter, some that don't. You can do things like, in this first step, remove these two links, you're sort of deleting those plaquettes. Then you can, say, fuse together a couple vertices, and you can keep going, fuse more vertices, fuse more vertices, and then here you're splitting apart two vertices, we're putting it in this form. So we've just sort of fully reduced the lattice, really gotten rid of all the geometric intuition that Raphael would have liked to have, but it's gone, sorry. It's very convenient to work with this.
I miss it.
It'll come back. So, our tensor network, I can now describe to you, is going to be a map, in general, from some lattice like this, that had, this is an example, has some lattice gauge theory, some matter links, and the tensor network is going to map that to something that's just a bunch of factorized links that live on the network. And all the constraints are gone. The tensor network has multiple steps. The first step is to fully reduce the lattice. That's maybe the main trick. So, we're going to proceed without loss of generality, assuming that we're given a lattice like this. So then I'll define how the tensor network completes the action on this guy, and then we'll, the full map will be take your lattice, first map it to this, and then do the steps that I'm about to tell you. So, as a warm-up, let's say we don't have matter. So we don't. So we just have this. There's no matter links anywhere, and so the goal is to map it to some boundary Hilbert space that looks like this. And the tensor network is going to act in a sort of trivial way, and maybe you don't even want to call it tensor network. It's hardly holographic. It'll have features we want, but without holographic encoding of matter, maybe it's not satisfying. But this is what it is. So it's just you take your state here, and then you just lift it, or isometrically embed it, into the natural pre-gauged Hilbert space, suggested by the lattice. So, for example, what I mean, for two links, remember, for these two links, if we're satisfying Gauss's law in the middle, I might as well label the state, a complete basis of states here is given by ket G. I just assign this group element to these two links. The embedding into the pre-gauged Hilbert space, it has to give me some state on two links. And what is that state? It's the one that would have satisfied Gauss's law at the vertex. So in this case, it's this one. The structure of the state doesn't really matter, but it's quite entangled. So now, what I want you to see is that this tensor network already satisfies a sort of holographic entropy formula. And to show you this, introduce an EREP basis. So this is it. We explained this ket G basis, but there's another conjugate basis. The other one's very useful. This EREP basis, which has the mu, I, and j there, and it's related this way. So this is the natural Fourier transform in the surface space. So again, these are the representation matrices. They form the coefficients. And so what's nice about this basis is there's this mu here quantifies the electric flux going through that link. So what we can do is write this two-link example that we just saw, but now in this new basis, it takes this nice form that will be informative for us. So if I assigned this Hilbert space, this ket mu ij, I've now introduced these names, little b and little b bar. Little b will be associated to this I index and b bar to that j index. This embedding map maps me to, what's important here is that, again, we have two links now, called capital B and capital B bar, and each of them have a k index. The second is the first one, the first and the second one, and they're maximally entangled. And this mu was sort of copied in this map, so both links have access to mu. It had to be this way because remember, physically mu quantified the electric flux. We're satisfying Gauss's law here, so you can measure the electric flux on either side. And what's important here is that, in general, so in particular in this state, as I'll briefly describe, the entropy of, say, this left link satisfies a sort of holographic entropy formula, where you get this area piece, or this entropy is associated to this edge mode. The edge modes being these new degrees of freedom that we included, like this, associated to this k index. So for example, here, I'm saying the entropy of B in this example, it's not just the entropy of little b, which would be associated with the I index. Here the I index doesn't look entangled at all, so that this S of B would be 0. But the entropy of capital B is not 0 because it has this entanglement in the K index with the other link. That is given by this area operator. So this is the sense in which even here we have sort of re-talking formula.
So is this pre-gauged embedding?
Yeah.
Is meaning?
Well, I'm defining it to be this way.
Okay.
Yeah, you could consider other embeddings, but there will be certain properties that you need to have. This is sort of the natural one that satisfies all these nice properties.
So just to make sure, here all the matter that you're discussing is not dynamical, right? It's you're just essentially the Chern-Simons formulation. You're just inserting by hand Wilson lines, right, at various points.
Yes, right. So I mean, technically on this slide, it don't matter at all.
Well, you write S of little b.
Oh yes.
It's a matter entanglement entropy, no?
In this example, it's associated to this I index, which is just some entropy you might have had physically associated to, say, this entity. Like this could have been entangled with something. It's not important for this.
Can I make a comment? So the S of little b here you can think of as the entropy of boundary gravitons. And like this model naturally has boundary gravitons in it.
Yeah. So I showed you an example with 2 links. With many links, you also get an analogous holographic entropy formula. And it turns out the area operator that you get still cares about the net flux, because that's what's measurable in both B and UR. So it would look something like this. If you were to compute the entropy of capital B, highlighted here in red, in the boundary Hilbert space, it would be correctly computed for you in this picture by this formula, where this expectation value of the area operator, the area operator is this ribbon area operator over here. Take note, it's a little more complicated than the bipartite case, because now the area operator quantifies the entropy of some edge modes. These some degrees of freedom that are essentially inserted there when you do the factorization that are more complicated. They're just multipartite entanglement in these edge modes. So there's lots of links in this one vertex.
So, you just said this, but there was you said before that there was an approximation of large flux somewhere.
Yeah, so, right, like the usual, it's analogous to the usual tensor large bond dimension.
I see, so you already, even in the previous slide, that was implicit there.
In the previous example, the formula I wrote was existing. So here I don't need that approximation either. I don't, because there's no matter.
Oh, sorry.
Yeah. With the more general setup, where we just have matter, we still want a map that does this, so it essentially maps us to all the boundary legs split apart, but the matter legs should be gone. You see they're not on this side. So we want kind of the same thing, but we can't just embed into the pre-gauge Hilbert space anymore. We also have to get rid of the matter sectors, the matter factors. And we do that by just hitting them with random tensors. That's the second trick. So after we take this state in this Hilbert space, embed it into the pre-gauge Hilbert space, then on each of these factors boxed in red, we get each individual one with a random tensor. Why? Well, the reason is that then boundary entropies satisfy a nice formula, shown by people in this room. And for suitable states, so this high flux approximation, you get a formula that looks like this. So in the picture, I've shifted around some matter legs to make it easier for me to draw. So I've just moved some up here. But you would have some formula like this. So again, the entropy of, say, these boundary legs highlighted in red, whenever in the boundary Hilbert space, would be correctly computed by taking the bulk state in this Hilbert space and using this formula. Where now S of B includes the entropy of the matter legs, say, on this side of the ribbon, on one side of the ribbon here, and not the other. And the A hat operator, again, is this A hat ribbon operator that would live here, in this case.
Sorry, Chris, I was zoned out for a second. Can you just go back a slide and explain what I was trying to talk terrible.
Which slide?
Yeah, just the setup. So we have, okay. So just what are the random tensors doing?
They are, okay, so they're acting on, there's a random tensor acting on this entire Hilbert space.
Yeah, okay.
One here, so within each red box, there's some Hilbert space, and they're hitting each of those individually.
But those Hilbert spaces are the vertex Hilbert spaces?
Yes, they're a little bit more because they have 2 links. There's 2 links and then a vertex Hilbert space.
Oh, okay.
Yeah. So altogether, just to summarize, the map is you start from something like this, and you want to end up with something like this. What the map does is it first fully reduces using a sequence. There's a finite amount of data required to tell you how to reduce. Then you map into pre-gauge Hilbert space. Then you act the random tensors on these matter guys, and you end up with this. And it satisfies the holographic entropy formula, like so, where this A hat operator is one of these ribbon operators. Now, I want to say something about a nice property that I alluded to last time I was here at Berkeley. A nice property is a non-commuting property of these A hat operators. So imagine that we have some lattice here, we have some matter, some of the vertices, and I'm going to pick two boundary regions that overlap. So like this red one, capital B, and this gray one, capital A. The red one, I don't know, maybe it's written operated something like this blue guy, maybe the gray ones is something like this green guy, for the state that I've suppressed. The point is that it just turns out there's no states that you can find in this Bulk-Hilbert space that are eigenstates for both area operators. These area operators, being these ribbons I put down, you can just show they fail to commute a leading order. They fail to commute, so there's just no eigenstates that for both of them. So this is a desirable property because, did I say this? This is a desirable match to gravity because, as Jeff and John and Aaron and Ning pointed out, this is what happens in gravity. You take two overlapping boundary regions, you can't find some state of the bulk that fixes both of their area operators. So the conclusion is, we have constructed a tensor network that satisfies the holographic entropy formula with a different kind of area operator. It's more like a target space area operator. And I claim this is essential if we want to combine tensor networks with the TQFT description of 2 plus 1 graph. Maybe we don't. Maybe that ruins all the nice geometric intuition that we had. But if we want to, and I think there are good reasons to, then we had to solve this problem. There you go. This had the additional nice feature that there are no simultaneous eigenstates of overlapping area operators, which is unlike other tensor networks, but like gravity. Thank you.
Hi, thanks for the nice talk. I have a vague and I hope not too nonsensical question. I think it's sort of generally true if you have these like finite gauge groups, then there's this duality between Chern-Simon theory in 2 plus 1 dimensions and conformal field theories on the boundary. And I guess this duality has also been studied to some extent, I think, in the condensed matter tensor network literature in different kinds of tensor network models, and I think they have all kinds of ideas about how this works. And can you maybe comment a little bit on whether there is some relation to the work that you've done, or whether there are sort of like interesting insights to be gained there? Or is there a connection to gravity with this, or is this like completely unrelated?
I think there are interesting insights to be mined there. That's one of the things I wanted to think about more. From our brief glimpse into that literature, I couldn't quite find anything very substantial to say, but I think there is something interesting there. That would be interesting to discuss more.
Maybe one comment we can make about that is that when you look at the correct Chern-Simon theory for gravity, the boundary theory is sort of an effective theory for the low energy stress tensor of the CFT. It's like something called Liouville theory, and like the Weismuller Witten theory of the gravitational Chern-Simon is Liouville, and Liouville is kind of the right low energy theory for ED CFT.
Yeah, the fact that you can do these manipulations to the lattice where you eliminate sides and at the end of the day you reduce it to a boundary just means that, doesn't it just mean that in the initial lattice description, the big lattice, that the local Hamiltonian is 0?
Yeah, so I think you're talking about this case without matter, first of all. So
yeah, let's say without matter.
Yeah, then I think the analogous with Hamiltonian would be much less interesting.
I'm just saying you never wrote down actually a lattice Hamiltonian.
That's right.
So I think technically your lattice Hamiltonian is just 0.
Yeah, we just have these constraints. Yeah, so we just have these constraints. We haven't added local time evolution. That is one of the things that I think should be done. It will be future work. way I would approach it is trying to add in some Hamiltonian on the matter and some coupling, or probably just some coupling to the gauge field, and then it would be less trivial in that sense. A prerequisite for having some model like that with nice behavior, I would say, is having a model that has this correct holographic entropy formula. So that was the one concrete problem we're solving right now. So,
yeah, so I also wanted to say that the Hamiltonian being 0 is a feature, not a bug. So in gravity, the Hamiltonian looks local, okay? But actually it's just a sum of constraints plus a boundary.
No, I understand that.
So that's exactly what's happening here. That you can write down a local Hamiltonian, but it will just be a sum of constraints plus a boundary. And this is talking about how to make a nice boundary term out of it. But also the fact that without matter you get this kind of trivial bulk is part of the reasons for it.
I was more commenting that it was more confusion about the beginning of the talk. That at the end of the day you want H-Wheeler to be 0, so therefore locally you want your Hamiltonian to reduce to the boundary somehow, right? And this is exactly what happens in this toy model.
Yeah. Yes.
Will your construction still work if you change your Chern-Simons to some other Chern-Simons, say, with other symmetry?
Yes, so I'll emphasize that we're working with sort of a toy model of Chern-Simons here. So I guess the continuum analog, well, I can write it maybe in the abelian case. It's like ADB plus BDA, not quite ADA. But I think that you could, yes, make this work with different gauge groups, like not finite, but compact, that should be easy. Non-compact, that would be desirable to match to gravity.
Yeah, I think I'm confused about, like, if you're talking about holographic correspondence, then you need some input which tells you you're looking at gravity. But if it works also for other gauge groups, then
yeah. No, this is a toy model very much in the vein of other tensor network toy models. So it's not. I'm not claiming that we're getting gravity here. We're getting a toy model that has. It's like tensor networks, but has one additional nice feature.
I see.
Yeah.
Yeah.
Maybe I have just one more question. Can you explain again why the ribbon operator, or which one of the ribbon operators that you wrote down becomes the Wilson line in the continuum limit?
Yeah, it's so the ribbons had the general ribbon was a little bit more general than a Wilson line. So it's this guy. If you just forgot about H, set H to the identity, then you get a basis of Wilson lines. Yeah, you get a Wilson line. Yeah.
And does this F gamma HJ have a meaning in the continuum limit?
Yeah. Yes. So in Chern-Simons, which is a little different from the continuum version of this guy, there's just Wilson lines, and so that would be the analog here. So Wilson lines and Chern-Simons match these ribbons here. In the continuum version of this guy in the abelian setting, where I know what the continuum is, I think it's just ribbon operators. Isn't that right?
Yeah, there are no ribbons in the continuum, but basically the point is that these theories don't quite have a Chern-Simons description except in the abelian case. So, but you should think of the ribbons as like the as like the lattice analog of Wilson lines. And then a central ribbon, which is the area of it, is a very special Wilson line.
Well, yeah, I think.
I thought that the ribbons with H equals 1, as you said, would be the Wilson line.
That's right. Yeah.
That's not true.
Wait. In general, in this lattice theory, that is true.
Okay.
In this lattice theory, you have to set H equals to 1 to get a Wilson line. In the Chern-Simons case, Wilson lines are all there are, and so if you're trying to match the action of this guy to the action in Chern-Simons, it's not just that maps to a Wilson line. It's also I believe. Okay, I don't want to say something I haven't talked too much about. I believe it's just these dual Wilson lines that you get if you set G to 0. I mean, yeah, if you set G to, if you sum over G. It's like the magnetic flux response, or what they call it, response. Yeah.
So like one case where you can actually make the mapping precise is like say in a Abelian proposal like this, which is related to the Chern-Simons series, which is something called a topological integration. And then like basically there's two gauge fields in the Chern-Simons. And then the Wilson line with H equals 1 is one of the Wilson line type. The ribbon with H equals 1 is one of the Wilson lines for one of the gauge fields. The ribbon values where G equals, where G is summed over, is the Wilson line for the other gauge field. And then like this is kind of like a combination of Wilson line for both gauge fields in that case. So it's kind of complicated. Like you can actually put Chern-Simons on the lattice with like parity invariant, but then it's just much worse to like go through. But like the structure is very similar.
I'm just wondering why, well, in SL2R Chern-Simons theory, we know we get distances. I think you referenced Alejandra's paper. We know we get distances by taking the logarithm of a Wilson line and appropriately accounting for the representation. I think the formula that you have for the area operator, which is also a distance, right, between two boundary points, is just a sum over, I forgot, it's on the next slide, I think.
This guy.
Yeah, so why is that the same as taking the log of a Wilson line with some representation?
So there's that guy, and then those guys get packaged yet further into this guy, where there's log language and everything.
Oh, I see.
Any last questions?
Okay, let's thank Chris again.